So, Anne, I always like to start with a little personal history. How did you get into astronomy?
Well, I think ever since I was very young, I remember 5 or 6, having moved from Center City, Philadelphia, where I could never see anything in the sky, to the suburbs where there were a few stars visible, that I was just really interested in what was out there. And I told my parents, I didn't even know the right name for the job. I said, I want to be an astronomist when I grow up.
Right.
And it's still in sort of my elementary school yearbook, astronomist as my
Wow.
career goal.
Okay.
And I was interested in a lot of things. I've always been interested in many different things, but that's been the one steady interest that I've had. And of course, the people, it's almost a cliche to say that the moon landings were a motivation,
Right.
but they were happening, they started happening when I was around 6 or 5 years old, 7 years old, and that had a tremendous impact
Right.
on me. I wanted to go.
Oh, yeah. Right. No, it's hard to believe, 50 years and we won't have been back. It is
Yeah.
kind of hard to believe.
It's depressing, although there are robotic means by which we've gone, so that's
And-
okay.
And were you also in the generation influenced by Sagan and his huge public footprint?
Yes, I confess to having had a big crush on him.
Yeah.
I look back now and all I see is nostrils, but at the time I thought he was so eloquent and
But
so
the
incredibly passionate.
70s fashions are coming back into style.
Oh, I hope not. I can do without the blazer and the patches and
Right.
the turtleneck. But he was a poet. I mean, he really could speak,
Mhm.
and he was so passionate about astronomy. And even though, again, in retrospect, the graphics are awfully cheesy on that
Right.
show, his explanations are second to none about so many of the issues he discussed. And
Right.
some of the concepts are now dated, I'm happy to say. There's been so
Mhm.
much progress since then, but
Mhm.
it's still a great program.
So let's talk about galaxies. What
Yes.
got you into galaxies? What made you an extragalactic astronomer as opposed to any other kind?
Well, it was very serendipitous in my life. Even though I knew I ultimately wanted to go into astronomy and astrophysics, when I started out as an undergraduate, I was in the dorm room. I met in my dormitory freshman year, and I had as my senior advisor.
And where was it?
This was at MIT.
Mm-hmm.
I knew I wanted to do a research project right away. Somehow that was in the air. That was one of the reasons that I went to a big school like that. And I had as a senior research advisor, actually it's a funny story, someone named Raymond Goldstein, who ultimately became a professor here in an entirely different department. But at that time he was studying chemistry and physics, and he suggested that I start a research project immediately if I could. And he said that there was a professor in the chemistry department who was doing chemical physics with lasers.
Mm-hmm.
And that sounded very exciting, very aesthetically pleasing to me. And I had a discussion with that professor, and I got introduced to the folks in the laboratory, and I had a wonderful experience for 2 years. I was there all the time. I wasn't in a classroom. It was beautiful. It was interesting. We were measuring dipole moments of
Wow.
molecules like
Mhm.
formaldehyde. I had a marvelous graduate student who advised me during that time named Pat Vaccaro, who
Mhm.
has become a very successful chemical physicist in his own right now. And I learned a great deal about doing research. That was really my first hardcore research experience. I knew I enjoyed talking about science and learning from scientists ever since I was in high school, where I worked for the Franklin Institute Science Museum,
Mm-hmm.
initially as a volunteer and later as a staff member. That was my great high school
Right.
job. But by the time I got to college, I just wanted to see what it was like to be a real scientist, and that experience for 2 years provided the opportunity. I got to go to a conference, I got to present the
Mhm.
results, and I was hooked. But getting back to my interest in galaxies, I did muscle up the courage to speak to my undergraduate advisor, Professor Field, at one point after those 2 years, to tell him that I loved the work, but I had always wanted to do something in astronomy, and that I would be looking around for another research experience in that field. And he said, well, I just got married. And that was a complete non sequitur, but he explained it to me as, well, I got married to the sister of a professor at Harvard University, who's a very well-known astronomer named Margaret Geller. So let me give her a call and we'll see if she has a research opportunity for you. It's fine if you want to do that. He was very, very encouraging.
Right.
And so that's the way it worked. And it turned out that the next research project I did was with Margaret Geller. I started with her as a junior. I got really interested in looking at maps of the distribution of galaxies in the universe. So at that time...
And this was at the time of the CFA survey or whatever?
Yes, that was so exciting.
And maybe just paint a picture of how little we sort of knew before the 70s about how galaxies are distributed or anything.
That's just it. So Margaret and John Hokra, a wonderful extraordinary scientist who unfortunately passed away in the last few years, had set out to actually measure that sort of elusive third axis in galaxy studies. It's easy to tell where a galaxy is on the sky, its X and Y coordinate, but astronomy, since we can't go places generally, requires us to be clever about how we measure the distance to things. And so they use the technique of redshift to measure the distance to different galaxies in what we consider today to be the relatively nearby universe to make a map of their distribution. And at that point, people really did not understand the details of how galaxies should be distributed. They could have been randomly distributed, much as you would scatter darts in our volume of the universe. It was known that there were clumps of galaxies called clusters, bound together by the mutual gravity of the galaxies and the dark matter. But how clumpy the universe was and whether there were regions that were kind of equally unclumpy was not well understood at that point.
Right.
So it really required this Herculean effort on their part to devise a scheme. Margaret in particular devised a scheme by which one could take a limited amount of telescope time and be efficient at sampling structure to get a sense of what the distribution of matter was. And for me, it was very exciting being very remotely a part of that, but it piqued my interest in the clumpy parts of galaxy structures, which were clusters of galaxies. And I kind of hung with that through projects that I pursued with her in graduate school.
And you mentioned the word Herculean, and it was, but so just to give people a sense of how much faster and more efficiently we can survey galaxies than they could, because it's dramatic.
Yeah, I mean, it seems like stone knives and bear skins when you talk about this. At the time, I participated again very much as a spare cog in those observations, but one would go to the telescope and not even use a CCD like people have in their cameras today, which are very efficient detectors of photons. These were old photomultiplier tubes. And the redshifts of galaxies, the distance to galaxies, were measured individually, one at a time, and you monitored the data as they were coming in and actually looked for enough signal to noise. And when you had a detection of absorption lines or emission lines that would enable you to characterize how much the light from that galaxy had been shifted to the red due to the expansion of the universe and therefore indicating its distance, you would stop the observation and move on to the very next galaxy. And these observations were typically minutes long. They might last a half an hour. They might last, in the case of the brightest galaxies, 5 or 10 minutes. Sometimes you needed to be on a galaxy, and this was with a 60-inch telescope or the original multiple mirror telescope on Mount Hopkins, which was much larger, quicker at getting galaxy redshifts. But it might take you in the course of a night, the whole night, to measure the redshifts for a whopping 10 galaxies. And you considered it a good day, and you went back and had a good sleep. These days, of course, people talk about measuring at least in the same part of the sky hundreds of galaxies redshifts at once, because the multiplexing capability has gotten so much better in astronomy. We use fiber optics to put fibers on the same positions in the sky where the galaxies lie, and if there are enough galaxies in the field and the field that you're seeing with your telescope is large enough, you can measure the lights from hundreds at once. And that's an extraordinary achievement, and what it's done is led to maps that are much larger across the sky And when attached to larger telescopes with more collecting area, it enables you to see further because you can measure the light of fainter objects. So the volume sampled in maps made of galaxies these days is considerably larger than it was then. But at the time, the discovery that Margaret and John made was that galaxies appeared to be distributed among the surfaces of bubbles or along filaments, such that when you looked out into the universe, you took a slice of it, you looked at a sample of these structures, you would see vast open regions of voids where there were very few galaxies, and other regions where clusters of galaxies lived, very much at the interstitial regions of the sort of bubbly or sponge-like structure.
Right.
And that was a big shock at the time. There had been intimations
Let's pause.
Oh, sure.
Oh, yeah. Just for the bombs. No, it's okay. The first part we can cut out. It's good to know what time it is. Given that I don't wear a watch. I have a phone and I never wear a watch.
Oh, yeah, it's pretty. Lots of bells.
Okay. You rewind interstitial structure.
Oh, yeah, so that the galaxies appeared to be clumped in clusters at these sorts of interstitial regions of the bubbles in this sort of spongy, almost frothy environment. And there had been intimations of this from smaller surveys in the past, but in the classic picture is worth 1,000 words, it became so clear in the maps that they made that that was the way in which galaxies were distributed in the universe. And it enabled, because of the details, people to say quantitative things about that distribution. How voidy was it? How clustered were galaxies? So my interest in galaxies oddly stemmed from those initial measurements of their distribution and their clumpiness, but they were still points to me on these plots.
Right.
At that point, we really weren't diving in to their individual properties and what that might have to do with their locations in this map, either in time or how clumpy an environment in which they lived. And for me, that came somewhat later when I was more of an elder in graduate school and as I entered my postdoc years.
So there's a sort of nature and versus nurture issue with galaxies. You sort of describe how that works. I mean, Hubble, arranged galaxies in a way and imagined evolutionary paths that are not all true, but there are still some interesting environmental effects.
Yeah, so astronomers love to classify things, and if you look at galaxies, you can see that each galaxy is completely unique. They're all different from one another, and yet there are some characteristics that many share. And so galaxies can come in the form of dwarfs or giants. They can come in the form of spiral galaxies with big star-forming disks, or elliptical galaxies that kind of look more boring, tend to have older stars, less star formation, look more like footballs. And one outstanding question in studying galaxies is why there are all these differences. And it's been a long-standing debate as to how much the differences that we see among galaxies is due to initial conditions at the time of their formation versus things that might have happened to them subsequently. So much as we have children and certain characteristics are there and maybe predetermined in their life genetically, so much else about what kind of people they turn out to be may depend on their environment, how they were raised, their parents, their friends. And we think that's true of galaxies, although like people in biology and studying human evolution, we don't really have a good sense of the relative importance of those two effects. Is it all about nurture, how they originated in the first place, where they formed, or is it about, during the course of their life, getting a few knocks here or there, being interacting with other galaxies, interacting with hot gas that may fill clusters of galaxies in space? It's still not clear. We think both factors operate, and they may operate to different degrees at different times and in different places in the universe.
And there's just as far as how the research goes, there's a conceptual issue, which is, you're talking about transformations and chronologies, and we just get this one snapshot of the universe back in time, and we have to reconstruct these histories with data. That must be a challenge too, to know that you've got that right.
That's a huge challenge, because as you say, we only have what light is arriving at us now to consider. We don't know for the most distant galaxies who were in effect seeing as they were then when the light left them, not as they are now when light is leaving them and hasn't gotten to us yet, how they're going to evolve directly into galaxies that are nearer to us and therefore older to us today. So we have to make a bunch of assumptions, and that's where things can get tricky in how you set up your experiment. So like anything in science, you have to be very clear about setting up controls to your experiment and asking the right questions so that the answers you get are unambiguous and meaningful. And unfortunately, a lot of studies of galaxy evolution can be very ambiguous, and it's through no fault of the scientists involved. It's because of this problem that you mentioned. We can't see how everything is right now. We have to make inferences connecting those that we have information on from the past with those that we have more recent information about, and that's very hard.
Of course, the problem is also an opportunity for clever observational design of an experiment.
That's exactly right.
But also, talk a little bit about, in this whole field of galaxy evolution and so on, the interplay between theory and observation. Is this field where observations have sort of always led the way, or are they informed by the theory?
Well, I think it depends on who you ask, and I'm an observer, so I would say that observations have, in many cases, been inspiring to people who do theory, but I also feel as if the theory has evolved significantly while I've been in the field and has gotten vastly more sophisticated and has challenged itself to make a broader spectrum of predictions. And I think there's more and detailed physics in the theoretical simulations that people conduct on their computers today than there has ever been in the past. There are still far too many simplifying assumptions. I think any theorist worth their salt will tell you that. But they're working all the time to make the theoretical models more realistic, and I think they've had some notable successes, and I think there are still many things in which they're hung up. But the field is data rich, and that's always when discoveries get made and the connection between theory and observation becomes far more interesting. There's so many data, so many kinds out there now, that I think it should be an inspiration for any young theorist entering the field to try to explain it all.
Well, and there's a flip side to that. I mean, you said every galaxy is unique, so another challenge when you're working in this kind of field is not getting into the weeds. I mean, how do you know what are the important global things or meaningful correlations, and what is just detail or weather
That's
or
right.
whatever?
And that's a place I think theory can assist you, because there's certain core properties that we know must be important in galaxies, like angular momentum, like mass, and then how you get from starting with those kinds of initial conditions to, wow, look at the details of the gas and the dust and the spiral arm of that particular galaxy is a big step. And right now, those kinds of comparisons are in their infancy, in the sense that we'd be very pleased as a community if someone were successful in producing the general properties of a spiral galaxy from scratch. It's bulge of mostly older stars, lacking gas, lacking dust, surrounded by this flatter disk of rotating gas dust and stellar material, which includes a lot of newly formed stars. That body has a certain mass, it has a certain angular momentum, but how do you get to that point from a bunch of particles in a box that feel each other's gravity? And which particles do you assign to be gas or dark matter or dust in a way that enables you to form stars at the right rates and produces beautiful image like we see it from Hubble Space Telescope is a huge undertaking, and people are trying.
And of course, you've alluded to it, but everyone studying galaxies is looking at these little white caps on this sea of dark matter. So let's move towards clusters and lensing and how you figure out the whole picture when you only see part of the picture.
Right. So I know you've already spoken to some folks about dark matter, but it is something that's so important in all the lives of people who do extragalactic astronomy and cosmology, because it's most of the stuff that we know about in the universe. at least that's the inference, as I try to stress to undergraduates whom I teach in introductory classes. What we know for sure is that there is extragravitational force out there that we can't explain. It's extragravitational force that holds stars in their orbits while they're orbiting galaxies, else the whole galaxy would fly apart. And we can't explain it with the gravity from the stars we see, so there must be extra gravity from either stuff we can't see, or a modification to the very laws of gravity is required. That's less in vogue right now as an explanation, that second one, so people tend to focus on what matter we're missing that could provide this extra gravitational force. It's also the case when we look at gravitational lensing. It turns out that general relativity predicts that mass should bend space, and that light must follow space. So when space is bent, the paths of light get bent as well. And it's very possible, if you picture sort of a bowling ball on a rubber mat, the classic example of mass bending space, and you were to imagine the light from a distant source behind that bowling ball of mass, which was between you and that source, that when you look at that source through the gravitational potential well, through that dent in space provided by this foreground mass, that light from the distant galaxy gets distorted in some way, as if that foreground mass were a lens, as if that foreground mass actually did bend the light of that distant object. And so that's called a gravitational lens. It's not just a theoretical construct. It's something that people know about, have observed happening in the real universe. And besides being fascinating in its own right and a demonstration that general relativity more or less works the way people imagined, it's also an indication of dark matter, because the degree to which that light is bent by the foreground mass is too much to explain if you merely consider the mass that you can see in the foreground. There must be dark stuff that additionally bends space to create the level of distortion that we see in background objects behind gravitational lenses. And so if you're interested in the properties of dark matter, looking at how those distortions occur, by how much, in what way, is a very useful constraint on not only how much dark matter is there, but how it might be distributed. And that ties back to our understanding of cosmology and how structure forms and evolves in the universe, and maybe even ultimately what the dark matter particle is. Because depending upon the properties of the thing that makes up the dark matter, which, by the way, we have very little idea about, that mass may distribute itself differently. And you can't see it directly. You can only see its gravitational effect on other things, either light or the orbits of things that it's capturing. And in the case of gravitational lensing, you're looking at its effect on light. And we use that effect to characterize it.
And if people used to seeing the little schematics or diagrams, should realize that this effects are quite subtle. I mean, lensing wasn't really a big game until good CCD imaging and Hubble and so on. So these are not easy effects to observe in detail.
That's exactly right. The spatial resolution on the sky afforded by Hubble Space Telescope, the ability to see detail, to take two things that are very, very close together or only slightly distorted and measure that separation or level of distortion, has been critical to understanding these problems.
And of course, physicists are doing their own lab experiments to try and detect dark matter, but talk about why clusters are really good labs for dark matter, for just understanding.
Sure, there's a lot of it in clusters. They're incredibly massive objects in the universe, and there are a lot of dark matter effects that you can measure that are borne out in clusters of galaxies. So I mentioned earlier that, in fact, one of the first ways dark matter was discovered in galaxies was to actually see that stars far from the center of the galaxy were rotating around the center of the galaxy too fast to be explained by the gravitational effect of all the mass you could see, that there had to be additional mass present to hold on to those stars in their orbit so that this galaxy would stay together. And that's true in clusters of galaxies as well.
And just as a sidebar, I mean, that's a pretty dramatic observation. And of course, it was 1930s. Why was that sort of shelved for 40 years? Why did dark matter not get on the table properly till the 70s and 80s?
Well, I think because the technology had to develop with regard to our being able to measure many galaxies in rich clusters of galaxies, or develop X-ray telescopes in space to see how hot gas was behaving in clusters of galaxies, to be able to understand the gravitational potential of clusters of galaxies and the masses of clusters of galaxies. So it wasn't until you could actually measure through many, again, we mentioned Herculean before, painstaking efforts to sample the individual galaxies in their orbits, or to look at clusters of galaxies as gravitational lenses.
It's okay. That's a quick one.
Okay. To look at clusters of galaxies as gravitational lenses, that it was possible to see the effects of dark matter in those systems.
So, and now you brought in X-rays and hot gas and so on. So there's a number of tools you can bring to play in a cluster, and you bring them all into play. How do they all contribute to the picture?
Right. So if you're interested in understanding how massive a cluster of galaxies is, and you kind of have to start there to know whether or not there's dark matter present, because again, it's always this comparison between the stuff you can see and how much gravity you can associate with that, and how much gravity there actually has to be present to hold on to everything that you can see. And there's always this discrepancy, that, and it's big, that's explained by the dark matter. So in the case of hot gas in clusters, that's an example of how new technology and the ability to sample a new wavelength that was previously inaccessible to you gives you very different intuition or new insight into a problem. In clusters of galaxies, it turns out that a lot of the mass that's in baryonic material, stuff made of neutrons and protons, is actually not in the stars in galaxies that we can observe, nor is it in the dust or the gas in those galaxies. It's actually in a medium, a hot gas medium, that fills the space between galaxies in rich clusters, and we call that various things, but intracluster medium is the generic term.
And why is it so hot?
Well, because the potential of the cluster, the gravitational potential of the cluster is so deep that it is tracing that gravitational potential, and that gas is 10 million degrees typically when it's measured. So those particles are moving very, very rapidly in the gas to give rise to these incredible energies that we observe.
And X-rays are the only vehicle or the only tool to really map that gas out.
Yes, to see that component, which is so hot that it emits in X-rays, you have to have an X-ray detector, and that detector has to be in space because fortunately our atmosphere blocks X-rays from reaching us here on the ground.
And if you, in this nice set of situations where you can piece together, where you have the lensing information, the X-rays, and you obviously can study the galaxies and their redshifts, what does it tell you about dark matter and how it's distributed?
Right. So what is measured, fortunately, is that the mass you derive from these different approaches to the problem, how much the light gets bent through gravitational lensing, how hot the gas is, how quickly the galaxies are moving in their orbits. Those three approaches to divining what kind of mass has to be present to create those effects more or less agree with one another. So that's the first step. You want independent methodologies to back up your assertion that, wow, there's a lot more mass here than we can account for. That's probably dark matter.
Which is, as an aside, that's really important because the explanations have a different physical basis in each case. So it's not like you're people who are skeptical of rotation curves or velocities and what they're really measuring.
Right, that's right. And so what's found is that most of the matter in the systems is stuff that has not been accounted for yet. And so you could be talking about systems that have the equivalent of 10 to the 15th sun masses, and yet what we see may only be 10 to the 14th sun masses. And so there's a huge factor that gets contributed by the dark matter.
And is this where we get our factor of 6 to 1 on dark matter to baryons?
Well, that's one place where one could potentially measure that.
And and then of course the other issue is if this is where you can do that experiment well and relatively easily, how do you know it's a fair sample of the universe?
Well, that's a really great question. So people don't just do it in one cluster. They do it in many clusters. They do it at many different times during the history of the universe.
Mm-hmm.
And so far, things seem to be hanging together.
Mm-hmm. Okay. So what's then, let's just talk a bit about the future. What are you excited about as far as current research?
Well, I'm actually excited about a project in which we're using gravitational lensing as a tool, not to study dark matter, but to actually study the formation of the earliest galaxies.
Mm.
So one of the problems right now, it has arisen from the great success of the Hubble Space Telescope and big telescopes on the ground at pushing back the time to which we can measure
Mm-hmm.
galaxies to within about 500 million years of the Big Bang. And that's an extraordinary accomplishment. These are very faint, challenging objects to observe. But we're still not quite back to a few 100 million years after the Big Bang, where their very first galaxies are thought to form for the first time. And it would be interesting if we could see that
Mm-hmm.
epoch, not only from the standpoint of understanding better how galaxies form, but also from understanding what the galaxies having formed do to the environment of the universe. If there are enough of those galaxies, if they have enough hot young stars in them that emit copious amounts of ultraviolet radiation, then that can disrupt the distribution of gas in the universe at that time and create bubbles and
Mm-hmm.
voids in it and change its nature and start a process that has ended with the universe that we see today.